Section 4.5, Projectile Motion. So, if you were to throw a rock into the air without gravity, as we know from Newton's laws, it's going to continue in a straight line until a force acts on it, does something to it, right? Just continue traveling in a straight line. But because we know that on the surface of the Earth there is gravity, when you throw something, gravity pulls it down as it's moving. So if you see, for example, if you fire a cannon in a straight line, right, without gravity, you get this dotted line. The cannon just travels in this particular direction. However, with gravity, over time, it starts to fall. Within the first second, it falls 5 meters. Within the second, it falls 20 meters. And by the third second, it's fallen 45 meters. And so what you wind up with is a curved path of an object as it's traveling through space. This is because you have some amount of horizontal push that causes it to move forward. It maintains that same initial horizontal velocity, assuming that there's no friction or air resistance. And so it continues traveling forward horizontally, but vertically, it falls. It falls like every other object falls in free fall. And if we combine those two motions together, you get a curved parabola. This is why when you throw something up in the air, it looks like a curve. It comes down as a curve. Now, any object that's propelled into motion and then is allowed to only move under the influence of gravity, we call that an object and projectile. So if you launch a projectile horizontally, you throw it straight to the right. As you can see in this image, and it's not perfect, but you see that each space horizontally is essentially equal. Vertically, however, the object falls faster and faster over time, and so you get a curved portion of a path, so that it's falling faster and faster, but it's traveling to the right with the same speed. If you launch a projectile at an angle, you're going to see similar types of paths, as you saw in that first image, but those paths, in some cases, will sometimes match up. So, for example, if you fire a projectile at 15 degrees or a projectile at 75 degrees, they're going to take very different paths to get to the exact same spot. Same thing goes for 30 degrees and 60 degrees. Different paths, exact same spot. And this is true for any angles that add to 90 degrees. So 76 and 14, for example. What you'll also see is that if you want to fire a projectile for the longest range possible, then you want to launch that projectile at a 45-degree angle. Now, all of these paths are taking into account the fact that there is no air resistance. And obviously on the surface of the Earth there is air resistance, and that air resistance matters. Okay, so if we launch, in order to get a projectile to go as far as we want it to go, with no air resistance, 45 degrees. But because air resistance does slow down the horizontal component of the velocity, it's going to slow it down horizontally. If you really and truly, in real life, want to get something to go as far as possible, you want to go from somewhere between 25 and 34 degrees. That gives you a little more horizontal speed than vertical, and gives you a little bit of horizontal speed to lose to air resistance. In general, if you try to fire it steeper, you're introducing more air resistance. And so you want to undercut that 45 angle if you're trying to do this in real life. The other problem you have is heavier projectiles are going to be much harder to launch at steeper angles. And so anything that's really heavy, you're going to want to keep that angle if you're going to launch it under 45 degrees. Even if 15 and 75 would land you in the same spot, assuming no air resistance, you would go for the 15 degrees rather than the 75, because it's much harder to launch an object at 75 degrees than it will be at 15. If we were to launch an object straight up from the ground with no air resistance, the time that it takes for that object to reach the maximum height of its flight is the same amount of time it takes for it to fall from that height to the ground. This is because the acceleration due to gravity is constant. As soon as you release it, gravity is pulling it down with a constant force. And that constant force turns it around in the first amount of time and allows it to fall in the second amount of time. But those two times are equal. Now in the next section, we're going to talk a little bit more about projectiles. But for a short-range projectile, the Earth itself is not really a factor, aside from the fact that it introduces gravity. But as you start talking about long-range projectiles and projectiles that travel faster, the curvature of the Earth plays an important role. It's important to understand how the curvature of the Earth would then influence how that projectile is falling. And that's what we're going to talk about in the next couple sections.